Weak acid, strong base titrations. When we're using weak acids in a titration, in order to calculate the hydrogen ions after a certain amount of strong base has been added, we have to deal with the weak acid dissociation equilibrium. This is similar to a buffer solution, so that means we're going to be able to use the Henderson-Hasselbalch equation in a lot of our calculations. It's important to remember that even though the acid is weak, it reacts completely with the strong base. So here's a problem. Let's consider the titration of 50 milliliters of 0.10 molar acetic acid with 0.10 molar sodium hydroxide. And the first thing we're typically asked to do is calculate the pH before the titration starts. So we want to calculate the pH before any sodium hydroxide has been added. So really, we're just calculating the pH of a weak acid solution. So let's take a look at what we need to do. We think about what's in the solution. We've got water and acetic acid. The acetic acid dissociates partially into hydrogen ions and acetate ions. We'd write our K expression, plug in our values. When we solve for X, X will give us the hydrogen ion concentration. And when we take the negative log of that value, that gives us the pH of the solution. So initially, our acetic acid solution has a pH of 2.87. Now we're going to start to add some base. And that strong base is going to react to completion with the weak acid in the solution. And then what's remaining after that reaction has been completed will determine the next step in calculating the pH of the solution. So here, because we're mixing two solutions together, we're going to need to know the moles of everything in our solution. So we've got water, acetic acid, sodium ions, and hydroxide ions in our solution. And remember that whenever we have a strong acid or a strong base in a solution, it's going to react. So in this case, our strong base hydroxide is going to react with the acid in the solution, which in this case is the acetic acid. It's going to react to completion to produce water and acetate ions. Now, since we're mixing two solutions together, we need the moles of hydroxide and the moles of acetic acid to do our ice chart. So we'll take the molarity of the sodium hydroxide and multiply it by the volume. That'll give us 0.00100 moles of hydroxide ion. And we'll do the same thing with our acetic acid. We'll take the molarity times the volume, and that gives us 0.00500 moles of acetic acid. Now we can make our ice chart. We know that the hydroxide is going to react to completion, and once that reaction is complete, we're going to have 0.00400 moles of acetic acid and 0.00100 moles of acetate ion. Now we've got a buffer solution. We can use the Henderson-Hasselbalch equation to calculate the pH. So we'll take the pKa plus the log of the base over the acid to calculate our pH. So our pKa is the negative log of 1.8 times 10 to the minus 5, which gives us 4.74. And we'll take the log of our base over our acid. Remember that the acetate is the base and the acetic acid is the acid. So we have the log of 0.00100 over 0.00400. That'll give us negative 0.61. So our pH is now 4.14. We move along in our titration, and now we want to see what the pH is after the total of 25 milliliters of 0.100 molar sodium hydroxide is added. So again, we've got hydroxide ions, water, and acetic acid in the solution. We're mixing two solutions together, so we want the moles of hydroxide and the moles of acetic acid. We'll make our ice chart, and we'll see again that our hydroxide is going to react to completion. We're going to be left with acetic acid and acetate after all the hydroxide has been consumed. And we're basically looking at a buffer solution again because we've got a weak acid and its conjugate base in solution. But this is a particular point in the titration. Because look at how many moles of acetic acid and how many moles of acetate ion we have after all of the hydroxide has been consumed. They're the same value. The log of 1 is 0, so the pH equals the pKa at this particular point in our titration. And we call this point in the titration the half equivalence point, when half of our weak acid has been consumed by the strong base that's titrated into it. And when you're at the half equivalence point, pH equals pKa. Now we're going to move along in our titration, and we're going to add a total of 50 milliliters of 0.10 molar sodium hydroxide. So we'll do the same steps as before. We want to calculate the moles of hydroxide and the moles of acetate ion. We'll plug those values into our ice chart, and our hydroxide is completely consumed by that weak acid in the solution. And we have no hydroxide and no acetic acid in the solution once this reaction has gone to completion. But we do have acetate ions. We can get the pH if we know the acetate ion concentration in the solution. So we'll take the moles of acetate ion, divide it by the total volume, and that gives us 0.050 molar acetate ion. That acetate ion will react with water to produce acetic acid and hydroxide ions. We'll plug our values into our ice chart. Since we're looking at a base, we'll need Kb, so we'll take Kw, divide it by Ka, and that will give us Kb. We'll plug our values into our K expression, solve for X. X will equal our hydroxide ion concentration for this particular example. So the negative log of that value will give us a pOH of 5.28. And if we subtract that from 14, the pH will be 8.72. Now we're going to move along. And we're going to have 75 milliliters of 0.10 molar sodium hydroxide. And when we look here, we're past the equivalence point, because we have more hydroxide that we're adding to the solution than we have weak acid to consume it. So we're going to be left with 0.0025 moles of hydroxide ions, which means that we can get the pH in a more direct way. We can take the moles of hydroxide ion, 0.0025 moles, divide it by the total volume of the solution, and that gives us 0.020 molar. That's our hydroxide ion. If we take the negative log of that, that'll give us the pOH, subtract that from 14, and that'll give us the pH. So the pH of this solution is 12.30, which is much higher because now our hydroxide is in excess.